Okay, so today we're going to investigate electrical circuits and current flow using this model here. So this will give us an analogy for how voltage, how current, and resistance, all these things behave. We'll also look at series and parallel circuits. So in this model, we have our battery. We have a difference in potential energy from the water that's sitting up high here down to this lower spot. So as it drops, there'll be a change in potential energy. That is just like the voltage drop that we would normally see. This drop is going to occur, the water will flow, the current will flow through this tube. So this tube is the equivalent of the resistance. So we'll just observe in this first case, we'll observe a case of a relatively high resistance, this is skinny tube. So when I close the switch, I'll let the current flow go, and so observe, we'll see a certain amount of time will pass for the water to reach this first green line. If we were doing this in normal times, I'd have somebody timing it and see how long it takes to reach, but we'll just do this qualitatively today. You'll see that a certain amount of time passes by for this level to charge up, and we'll stop. So in our next configuration, we have the same voltage drop, the same change in potential energy, the change in height for the water. What's different now is we have a wider tube. This wider tube effectively acts as a lower resistance. So if we do this now, we'll see with the same voltage and a lower resistance, when we open the switch, let the current flow, you'll see we get a much higher current flow. And it's not perfect. There's actually there's a little choke point in here, but you can see it filled up much faster. With this lower resistance, we had much more current flow. We filled up much faster. All right. Okay, so now we have a series circuit. I've taken two resistors and I've connected them in a chain. This is how a series circuit would work. Note in this case, the voltage drop, we don't get all the voltage dropping across one resistor. We'll drop part of it across the first resistor. We'll have the same drop across the second resistor. Now, when I turn these on, there's much less current flow because each resistor has just half the voltage drop across it. So when I run this, you'll see it's going to take much longer time to charge up our battery here, to fill it, because there's much less current flow given the fact that the voltage drop is occurring across each of these. Now, I won't show it in this video. If we had two different resistors with different resistances, to keep the same amount of current flow, you'd have to have a bigger drop across the higher resistance, smaller drop across the other one. That is how we see the series circuits work. The same current, the same flow is occurring through both of them. The voltage drops will adjust so that you keep the same current flowing. Our final configuration, we have a parallel circuit. Now we have two of these resistors. They're connected side by side. Each of them are getting the same voltage drop. They're getting the same change in potential energy from the high point down here to the low point. Now that I've got two of them, we have two paths for the current to flow. So when I turn this on, you'll see that we get more current flow than when we had just a single resistor. Each one has the same voltage drop. They're each going to get the same current. Therefore, we will get twice the amount of current with this given voltage drop. If we were to do this differently, if I put a fat pipe in here or a lower resistor, still connected in parallel, we have more paths for the current to flow. We have a lower effective resistance. We have a higher current. The easy way to do it is take the voltage drop across each of them individually, find the current through each one, add the currents together. That will give you your total current. And that is how we model parallel circuits.